Can we completely classify surfaces just by studying loops on them? From spheres to tori, topology gives a powerful algebraic answer. To understand how, we first have to define what a standard mathematical surface actually is. In topology, a surface is a Hausdorff space that has a countable basis, but the defining characteristic is local homeomorphism. This means that if you zoom in on any single point on the surface, its immediate neighborhood looks exactly like a flat, open subset of two-dimensional Euclidean space, R squared. That local property creates a global classification problem. If every surface looks flat and two-dimensional up close, local geometry cannot help us distinguish a continuous sphere from a multi-hole donut from a distance. We need an objective way to tell them apart without relying on visual intuition. We need to find an algebraic fingerprint that uniquely identifies the global structure of these spaces. Algebraic topology exists precisely to solve this. It provides the machinery to translate continuous geometric shapes into specific algebraic equations. Our primary classification tool for this translation is the fundamental group, denoted as pi1 of x, x0. To build this group, pick a specific base point, x0, and draw a closed loop, f, that starts and ends precisely at that base point. The core mechanism here is path homotopy, the continuous deformation of one node into another, while keeping that base point entirely fixed. If you can slide, stretch, or warp one loop into another, without breaking the path or leaving the surface, all of those variations form a single equivalence class. To turn these classes of loops into a mathematical group, we need an operation. Here, the group operation is concatenation. You travel along the path of the first loop, and then immediately travel along the path of the second. This group structure allows us to test the global properties of a space. By identifying these loops and their relations, we transition from examining shapes to calculating properties. If we apply this loop machinery to two separate spaces and calculate fundamental groups that are not algebraically isomorphic, it is mathematically impossible for those two spaces to be homeomorphic. Let's test this machinery on the simplest closed surface, the n-sphere, or Sn, for dimensions where n is greater than or equal to 2. Theorem 59.3 in Munkres states that the n-sphere is simply connected. This means its fundamental group is trivial, written as pi1 equals 0. Every loop can be shrunk down to a single point. This diagram illustrates the proof method. We designate a point P as the North Pole, then use stereographic projection to flatten the punctured sphere onto a plane. Any loop can be slightly deformed to avoid passing through that single pole point. Once the loop avoids the pole, we map the rest of the sphere via stereographic projection. The entire loop now lies within a space that is homeomorphic to flat Euclidean space, Rn. Euclidean space Rn is simply connected. There are no holes in it, so any closed loop drawn there can be continuously shrunk down to a single point. Because the mapped loop is null homeomorphic in Rn, the original loop we drew on the sphere is also null homeomorphic. The topological math proves our baseline. The sphere yields a trivial fundamental group. We step up the complexity with our second example, the torus, defined as the product space S1 cross S1. While Theorem 60.1 computes this by evaluating product spaces, that method becomes unwieldy for shapes with multiple holes. We need a more scalable tool, the polygonal labeling scheme. Look at the left of Figure 73.1. Instead of 3D curves, we start with a flat 2D unit square, I squared, the foundation for a quotient space. A pasting mapping, H, maps the edges onto each other, folding the 2D surface into the 3D torus. To find the fundamental group, we trace the path of the boundary loop running counterclockwise around the perimeter of that original flat square. Following the arrows on the edges gives us a specific sequence. We travel A0, and then B1, then backwards for A1, and backwards for B0. We translate this geometric perimeter traversal directly into formal algebra. An edge traveled backwards is written as an inverse, yielding the relation alpha inverse beta inverse. Flattening a 3D surface into a 2D polygon strips away the visual complexity. It allows us to extract the algebraic DNA of the shape directly from how its boundary edges are glued together. To process this polygonal word into a final fundamental group, we use the mathematical engine known as the Seifert-Van Kampen theorem. When the pasting map glues all the corners of our square to a single point on the torus, the outer edges form what topologists call a wedge of circles. The algebraic equivalent of this edge structure is a free group, generated by our distinct edge labels, alpha and beta. We will call this free group G. The solid interior of the polygon imposes a topological constraint on our loop. Because the path must span Munkres, the interior forces a quotient operation onto the free group. Our boundary word specifies how that constraint is applied, generating the least normal subgroup N. The final fundamental group is the quotient group G mod N. Because the boundary word is a standard commutator, this resolves to a free abelian group of rank 2, Z cross Z. The Seifert-Van Kampen theorem acts as an algorithmic translator. It turns visual edge pasting instructions into specific normal subgroups that we quotient out to find the final algebraic group. This machinery proves its worth when human intuition fails, such as with our third example, the projective plane, or p squared. Geometrically, the projective plane is defined as a quotient space obtained from a two-sphere by identifying every single point with its exact opposite or antipodal point. It is impossible to visualize this shape correctly in our standard physical dimensions. It cannot be embedded in R3 without passing through itself, creating an immersed surface. We bypass the 3D visual completely by looking at the formal proof in Corollary 60.4. It confirms that the projective plane yields a specific, finite group structure. Running this two-letter word through our quotient machinery immediately gives us the answer. The fundamental group of the projective plane is isomorphic to Z mod 2. This reveals an order 2 group. It tells us structurally that a loop must travel across the space exactly twice before it can be shrunk to a trivial point. Our algebraic tool maps the non-orientable surface flawlessly without requiring us to picture it. Finally, we scale this scheme up to complex geometries, the n-fold connected sum of tori. If we have a 4n-sided polygon, the boundary tracing creates a repeating labeling scheme, A1, B1, A1 inverse, B1 inverse, all the way to AN, BN, AN inverse, BN inverse. Looking at figures 74.8 and 74.9, we see exactly how this long algebraic string connects to physical geometries. A polygon with 8 or 12 sides maps directly to a double or triple torus. The math scales as needed. Every new physical hole in the surface translates to a new set of free generators in our algebraic equation. No matter how many holes a compact surface has, its entire topology is captured entirely by a single quotient relation derived from its flattened edges. The fundamental group serves as a formal invariant to distinguish these surfaces mathematically. We establish a direct translation where the physical holes in a surface equal the free generators in our algebra. Comparing our three subjects shows this clearly. The sphere has no polygonal label and a trivial group. The torus has a 4-letter boundary word, resulting in Z times Z. The double torus expands into an 8-letter scheme, yielding a quotient of 4 generators. The specific pasting instructions required to build any surface dictate the exact normal subgroup we must quotient out to classify it. Algebraic topology succeeds by encoding continuous geometric deformations into discrete, solvable algebraic structures. If you found this helpful and want more clear explanations from standard books like Munkres, don't forget to like the video and subscribe.